Soccer players, football players, and badminton players, and other athletes are able to pass and receive up the ball with amazing precision. How do they do it?
They do it with the help of velocity vectors, which describe both the direction and the speed of their movements. But before we dive deeper, let's first understand what is a vector. A vector is a quantity that has both magnitude and direction. It is an addition of a scalar, which only has magnitude, which tells us how far or how strong something is. To describe vectors in a space, we use Cartesian coordinates, like points on an xy plane or axis, to locate the position or movement of a vector. Vector notation is then used to calculate and represent vectors, with letters and arrows showing both the magnitude and direction. Let's put that into perspective.
When an American football is thrown, the scalar quantity is the speed at which the football is moving. The velocity is the speed and the direction at which the football is moving. This forms the velocity vector of the football. When an athlete moves from their original position to a position where the football can be passed freely to reach a teammate, the speed and direction they move from their original point to their new position creates an additional vector, the athlete's velocity vector. If the athlete uses the same amount of force and throws the football in the same direction as before, the football will end up in a different position that can be calculated using the parallelogram rule, where the football's velocity vector and the athlete's velocity vector are combined to find the resultant vector that shows the football's actual path with reference to the athlete's original position. The resultant vector is the true final velocity of the football in this case. With the help of the resultant vector, we can accurately estimate the final position of the football.
Example of a parallelogram rule. If the ball thrower runs from point A to point O, while the person catching the ball runs from point B to point C, the resultant vector when the ball is thrown from point O to point C. To find the magnitude of the resultant vector, we can employ the parallelogram rule formula, the square root of OB squared plus OA squared plus 2 times OB times OA cosine theta. To find the theta, we tangent inverse the height of the parallelogram divided by AC, which gives us 43.363 degrees. Hence, now that we have the values of theta, the resultant vector will be square root of 9 plus 4.5 squared plus 2 multiplied by 9 multiplied by 4.5 cosine 43.363 degrees, which will give us a magnitude of 12.65 units.
Through the air. Now the speed of the shuttlecock tells us how fast it's moving. That's a scalar quantity. But when we also include its directions, we now consider it a velocity vector. This velocity vector shows both how fast and where the shuttlecock is going. But nature often adds a twist, the wind. It will bring its own the speed and directions. This wind vector interacts with the shuttlecock velocity vector, changing its flight path. To understand where it will actually go, we can use a triangle rule for the vector by combining the shuttlecock velocity vectors with the wind velocity vectors. We find a...
Okay, now moving on to the calculations again. How do we calculate the magnitude and the deviation with the triangle rule? We can let the wind speed be the height of the triangle at 4 units, and the initial velocity be the base of the triangle at 7.5 units. To find the magnitude of the resultant vector Fr, we can use the Pythagoras theorem, in which the sum of the base of the triangle squared and the height of the triangle squared can give us the resultant force squared. We can then square root the value to find the magnitude of the resultant force, which gives us 8.5 units. To find the angle of deviation, we can use inverse cosine the height of the triangle divided by the base of the triangle, which will give us 28.07 degrees.